So let me just look at something. So if I take the number 30, right? One thing I can do with this is I can write it as the product of two things, of its factors, right? So let me say I'm going to write 30 as 5 times 6, right? And another thing I might be able to do is I'm going to write 6 also as 3 times 2, right? So I can write 30 as 5 times 3 times 2, right? And basically the idea with this is now I can't do this any further for 5 and 3 and 2, right? So, and what we're going to do in this section is talk about why we can write any number like this in terms of the product of factors that you can't go anymore with this. So now we're going to call these things prime. So let's do as we've done for everything in this section, talk about a definition. So a whole number greater than 1 is called prime if its only factors are 1 and itself. Okay, so for example, 30 is not prime because I can write it as 5 times 3 times 2. There's some factors like that. However, 2 is prime because the only numbers that I can write it as is 1 times 2. The same for 3 and the same for 5. Okay. And a number that is not prime is called composite. Composite in just English just sort of means made up of other things, like materials or something. There's something called a composite materials, just made up of other things. So 30 is a composite number, like that. Okay, I've got another video on actually finding prime numbers, and I would go take a look at that. So we're going to basically say that we know how to find some of these, like 2, 3, and 5 are examples like that. And but I want to look at a little bit more about these things. So we have a little lemma here. Every whole number n greater than 1 is a multiple of a prime. All right. So, by the way, I should have mentioned this before. I've got this here, greater than 1. We said this again, greater than 1. Basically, what we want to do is 2 is going to be our smallest prime number. It makes lots of things convenient. So this is just like part of how we decide to define things. So this is part of that as well. Okay. So one of the things you can look at, so every whole number is a multiple of a prime. So I can look at this example here, right? 30, I can write as 5 times 6, right? 5 is prime. Right? I could also have written it like 2 times 15, 2 is prime. So this has more than one example on it. Let me try another one. So 28, right? And I can write that as 2 times 14, right? And we know we've got 2 is prime. I can also write it as 4 times 7. Okay, this does not mean that every product has a prime. So for example, if I said 16 and I'm going to write it as 4 times 4, these are not prime. But what this says is that I can write it as the multiple of a prime. So I can write it as 2 times 8. All right. I'm going to prove this thing because this is pretty important. Proof of the lemma. All right. So write down all factors of n and call the smallest greater than 1p. Okay. So maybe let me come back over here. Right. 28 I can write as 2 times 2 times 7. Okay. This one has 2 repeated twice. But in this case, I would just say 2 would be p. The same thing over here, say something like that. If I had, let's say, 63, which is 9 times 7, 3 times 3 times 7, right, p would be 3. Okay, so I'm just going to say, call the smallest one p. So we're going to prove this by what's called contradiction. Prove p is prime, sorry. All right. This is a really nice technique in that what we're going to do is we're going to assume it's not true, and then we're going to get some kind of a conflict, and then by basically what that implies is that the assumption that it wasn't true is not true. Okay, so assume p is not prime. Okay. So if it's not prime, then we can write it in terms of a product of factors. Then p can be written as r times s, right? And r and s are both sort of whole numbers that are smaller than p, right? But r is less than p and s is less than p. Come back to here. This is the continuation of the proof. But and we assumed that p was the smallest factor. Okay. This is a contradiction. So p is prime. Okay, let me go through that again for a second. And boink. Proof done. Okay. All right. So we're going to prove that it's prime by contradiction. So I'm going to first of all assume it's not prime. right? We call the smallest factor greater than 1 p. If it's not prime, we can write it as the product of two factors, where they're both like bigger than 1. But these are both, that means they're both less than p, right? If I've got the product of two whole numbers, one of them's less than p. So basically, but we assumed that p was the smallest factor, but we've got two other ones that are smaller than it. So therefore, p is prime. Okay, now this doesn't seem like that important, except for what we're going to see is a really very important theorem, and we're going to use this. This is called the fundamental theorem of arithmetic. Seems pretty important, right? Fundamental theorem. It is pretty important. Okay. Every whole number n, which is bigger than 1, can be written as the product of prime factors and this is unique up to the order of the factors. Okay. Okay, so basically what I'm going to do is I'm going to be able to say any number n here I'm going to write as the product of its prime factors. All right, so let me write down a couple of examples here before we do this proof. So 30, we already did this, is 2 times 6 times 5. Right. Let me do something like 48. Right. So 48, typically one thing you can do is I can say, well, this is say 4 times 12. Right. And 4 I can write as 2 times 2. 12 I can write as 3 times 4. So 2 times 2 times 3 times 2 times 2. Okay, and then these are all prime. So what we're doing here is we're just able to write this down in terms of product of prime. And then this is unique up to the order of the factors. This is exactly the same as if I would have written it as 2 times 2 times 2 times 2 times 3. Right? And we're also going to start writing this as powers. So 2 to the 4th times 3. This is called the prime factorization. We'll get to that a little bit. Okay. But these are not different than each other, right? They're just different orders. Okay. But what this is saying is this is unique. You get exactly a unique thing. Proof. Okay, here's what we're going to do. By lemma 1, or lemma whatever that was, the one I just erased up here, let's call it lemma 1. Should say we can. So I can write my number n as p1n1, where p1 is prime. Okay. if n1 is 1, then n is prime. Okay, because that's the definition of a prime, is the only two factors are itself and 1, right? So basically, if when I do this and I come up with one, like just one prime, then the original was prime. All right. If not, right, n1 is p2 times n2 by the same lemma we just did. What does that mean? Again, I can take any number and write it as a prime times something else, where the prime is the smallest. So, capital N is P1 times little n, which is P2 times N2. Continue this until n sub k equals 1. Just like up here, eventually we get the 1, we have that, and n equals p1 times p2 times pk. Okay. All right. So basically the big piece of this is like the most important thing here, is that this n, any n now I can write as the product of primes. So we'll do some more examples in another video. Okay, so that wraps up sort of intro to prime numbers and the fundamental theorem of arithmetic.